Hello, welcome back. In the previous lecture, previous two lectures, we were looking at applications of pigeonhole principle, right? And then while we were doing this, we came across a small application where we showed that if you take six or more people, then among these people you can always find either three people who know each other, who has met each other, or three people who are strangers who has never met each other, right? Now, this result is one of the starting points in a huge area in combinatorics called Ramsey theory, and there can be many generalizations of this, and these generalizations are kind of also related with pigeonhole principle in some sense. We will see that in a moment, and try to look at today's lecture with the more general theorem of Ramsey, and then we will see that how it is a generalization of our pigeonhole principle. Okay, so what the theorem that we proved was saying that if you have a graph, right? We also looked at the graph version of the same. If we have a graph and the graph has six or more vertices, right? You take a six vertex graph, for example, and you color, and you put all possible edges, right? You consider the complete graph, and then you color all the edges with just two colors, right? Then we were able to show that you will find either a red triangle or a blue triangle, right? A complete graph on three vertices with all edges having red color or blue color. It's mutual strangers or mutual friends. Now, suppose instead of six, suppose we had only five, right? So we use the fact that we had six vertices at least to apply the pigeonhole principle. Now but that doesn't necessarily mean that smaller graphs you cannot have such a property. But let us now show that if you have only five vertices in the graph, then we need not have this property. Okay? So I'm going to give a five vertex graph. See, here is a five vertex complete graph, and I have given a two coloring, right, of the edges. All the 10 edges are here, and then this five edges, five cycle, I give red color, and then in the inside I look at this five edges and then also give blue color. So this colors all the edges, but the point is that you cannot find a triangle of the same color, right? You cannot find a single color triangle, right? If you take any of the blue edges, they never form a triangle, right? They form a five cycle, and outside also it forms a five cycle. So we needed at least six, right? So 6 is the smallest number with this property. Now, if you have anything larger, we already saw that we always have the property, because once 6 will do this, you can always take a subset with 6 and that has this property. The entire set has this property. So, and we use pigeonhole principle for the 6th case like this, right? You had at least 3 of the same color, and then look at the edges between those 3 neighbors, and those neighbors, you can see that whichever way you color, it either creates a triangle of either red, which is or blue. Now, so this talks about coloring the edges of a triangle with two colors. What if we allow more colors, right? See, what essentially the Ramsey theorem was saying, we said that when when you try to make things more chaotic, as far as the the set that we are considering is really huge, then you can still find some order within that, right? So here is the question. That suppose I increase more colors, then what can you say, right? Suppose I say that I use, instead of two colors, I use k colors. So if you take k colors and color the edges of a complete graph with k different colors, what is the smallest number of vertices which can guarantee there will be a complete graph of, let's say, either triangle or something larger, like 4 vertex complete graph, 5 vertex complete graph, whatever, where all the edges have the same color, right? You can ask this. Now, one question is that does there exist such a small number, right? Such a not small, such an integer, such that after that you can always guarantee this. Now it turns out that there exists always, so but this needs proof, and we are not going to prove it at this moment, but I will let you think about it and maybe try to prove for some special cases. So just 2 colors with a larger number of clicks. Okay, so here is the general question or the theorem of Ramsey in a slightly more general form. You will find even more general form later. So let C1 to Ck be k different colors and n1 to nk be integers where ni at least 2. Okay. Then you can find some integer, okay, r of n1 to nk. Okay, so n1 to nk are the numbers. So in the problem that we looked earlier, we were looking at we need a complete graph on 3 vertices, which is all blue, or 3 vertices, which is all red. Right? Here you are saying that you have n1 vertices, n2 vertices, etc., nk vertices. Then you are asking for either a complete graph on n1 vertices where all the edges have color C1, n2 vertices all the edges have color C2, or nk vertex a complete graph where all the edges have color Ck. Okay, so the claim that the theorem says that then there exists an integer r of n1 to nk, which let's say p, such that any edge coloring of the complete graph on these many vertices kp with the k colors C1 to Ck must contain either a kn1 colored C1 or a kn2 colored C2 or a knk colored Ck. This is something which you cannot avoid. So as far as the number is large enough, right? As far as the number is larger than r of n1 to nk, okay? Yes. So yeah, I mean, yeah. So fine. Yeah. So when p is larger than r of n1 to nk or whatever something, then you can always consider the some subgraph, and then that subgraph has this complete subgraph of same color inside, then the entire graph has this as subgraph. So that is okay. So we don't have to worry about writing in a different way. Okay, so this is the general form of Ramsey theorem, right? You have a k coloring of the edges of the complete graph, and then you are asking, can you find smaller some complete graphs of certain orders where all the edges have the same color. Now, so in using the same notation, what is R of Mn? Right? R of Mn says that you are looking for a complete graph. So you are looking at 2 coloring because there are only 2 arguments here, and you are looking at a complete graph on m vertices as a subgraph with the first color, all the edges having the same color, or a complete graph on n vertices where all the edges have the second color. Right? So this is Rmn. Okay. Now what we proved earlier was that using P-general principle, R of 3 is equal to 6. Okay. If you have 6 or more vertices in the graph, then you can always find a triangle, right, of the same graph. Now what is R of 2? Can you think of this and try to solve it? Very easy, I think. You can do it. What about R of 3, 4? Okay. So R of 3, 4 is equal to 9. Now the question is that can you prove it? Can you come up with a proof that R of 3, 4 is equal to 9? Again, these things I don't know. I mean, maybe it's much more difficult to prove. R of 3, 5, R of 4, 4, and R of 3, 3, 3. Right? This. So you are 3 coloring now, right? then show that if you have 18 vertices or more, then you will contain a triangle of first color or second color or third color. Okay, so these numbers we already know, right, for these small values. Now what about R of 5, 5? Okay, so R 5, 5 asks for a complete graph on 5 vertices as a, right, like something like this, complete graph on 5 vertices, but all the edges must have the same color. Okay? So a complete graph on 5 vertices where all the edges have the first color, right, red, or a complete graph on 5 vertices where all the edges have the color blue, right? Now, what is the smallest such number with this property? Well, we still don't know the exact value. Okay? What we know is that it is between 43 and 49. Okay, R55 is between 43 and 49. Now, what is R66? Right, you can ask. Now, I want to tell you a story. Okay? So this is a story. There is a story of what Paul Erdős, a very famous mathematician, many of you might have already heard about him, used to say. Okay, so when he talks about problems related to Ramsey number, he will say this following joke. Okay, but half serious, not just a joke. So the joke is the following. So he says that see R55, he believes it is very difficult to compute. Okay, very difficult to find exactly. We still don't know, as I told you, we still don't know what is exact value. But he says that suppose some alien forces, right? Alien forces come, like from some other galaxy. They come here or some other star system from our galaxy, but they are vastly more superior to us. They have all kind of technology. They can have it. They have something like what you see in this kind of sci-fi movies, right? You can just destroy a planet, with some weapon. So they are so powerful that they have such weapons, and they come here, and then they tell us that, well, we will let you leave if you tell us the value of R55. Okay, then he says that maybe we can put all our forces together, put all the computers to work for the same question, do some parallel computation, all the mathematicians work on their own, or work together to find out this value. Maybe we can save our planet, right, by finding the value and telling them the correct value. But suppose they ask for R66, just kill them before they even think of attacking us, because he says that it is not, at least he believes that it is not possible. Okay, not with the current knowledge and techniques and all we have. It's what he says. So yeah, so finding Ramsey numbers precisely is a very, very difficult problem. So people try to find bounds like upper bound, lower bound, etc. We will not go into any of those things. Not in this course. Or maybe at the end we can try to prove some lower bounds or something, or even upper bound maybe, using some arguments. Okay. Now some new techniques that we will learn maybe. Now on the other hand, we can find some not necessarily great looking, but some kind of upper bound without much difficulty. So for that, what I want to do is I want you to show that Rmn exists. Okay, well, at least try. Okay, so try to show that Rmn exists by showing an upper bound for it. See, what we're saying is that if a number is larger than Rmn, then of course we can guarantee that there will be a M complete graph or an N complete graph of red color or blue color, right? But when we say we find an upper bound, right, we are saying that okay, we don't know precise value of Rmn, but if you make sure that if the number is maybe much larger than the actual value of Rmn, right, it's much larger than, let's say, 20,000 m times n or something, or like 20,000 whole power m times n or something like that, right? Whatever, some number, or m raised to 2 raised to m and 2 raised to n or something. Then can you say, at least in that case, that anything larger than that will contain a m complete graph? So this kind of some weird much larger number can be an upper bound, saying that anything larger. So therefore it says that it exists, because we know that as far as you go above this, you are guaranteed. So which means that it exists definitely. We don't know what is the smallest one, but we know still such things exist. So prove that Rm and exists, right? Rm and exists by showing some argument, maybe induction or something that you know. Well, anyway, think about it and try it. I'm not giving it as homework, but it's not part of this work that we are looking at, but it will be instructive and interesting. Okay. So here is the question. Can you prove that Rmn exists? That is, for every m belongs to n plus, there is a positive integer Rmn such that a red-blue coloring of the edges of complete graph on p vertices for p greater than or equal to Rmn must contain a copy of Km for all whose edges having blue color, or a Kn where all edges are red color. One of these must be present. Okay. Now, an even more generalized question that we can ask. Okay, so what's called Ramsey theorem for hypergraphs. So when we talked about graphs, what was a graph for us, right? The graph was basically a set. We had a set of vertices, right? And then some two element subsets, right? So we were restricting ourselves to binary relations. Now suppose we instead of binary relations, we look at arbitrary relations, right? So we're talking about arbitrary subsets. Then you have what is called hypergraphs. Okay, so a hypergraph is basically a set together with a collection of subsets. Okay, so E is just a collection of subsets. We don't even say what kind of sets are there. So elements of S are called vertices and the sets are called hyperedges. So here is an example, right? You have this 5 vertex, 5 vertex graph, hypergraph, and where now I have these edges, right? So these two elements of set is an edge. These two elements of set is an edge. Then there's three elements of set is also an edge. Okay, so this so what if you give numbers like 1, 2, 3, etc. to this, like say this is 1, this is 2, this is 3, this is 4, this is 5, then our vertex set is the set 1, 2, 5, right? Then what are the edge sets? The edge is basically 1, 2, 3 is some edge, 1, 2, 3 is an edge, then 4, 5 is an edge, and then 3, 4 is an edge. So 1, 2, 3, 4, 5 and 3, 4. So these are all edges of this hypergraph, right? So this is an edge, right? 1, 2, 3. So in earlier we had only two elements of sets, but now we can have any kind of subsets. You can even just have one, right? One element subset. That is also allowed. When you let's say that you have this, right? This is one. So I can say that this is also an edge. So this is okay. Now, yeah. Now, when we have this kind of arbitrary subsets, it's even more difficult to deal with. So we'll often look at a slightly more restricted version, where we call uniform hypergraphs. So a k-uniform hypergraph is basically a collection of k element subsets of S. So we only look at k for some fixed k. Like when it is two uniform hypergraph, it is just a graph. When it is three uniform hypergraph, then you have all the edges have three vertices inside, right? All the edges have three vertices inside. So here is an edge, here is another edge, here is another edge, and then here is another edge. So, yeah. And then when we have all possible 3 element subsets part of this edges, then it's called a complete T uniform hypergraph. So I denote it by KTN or KNT. Okay. The complete T uniform hypergraph, set of all T element subsets of an N element set. So this N says the subscript says the number of vertices and the superscript says the cardinality of the edges, right? Not cardinality of the edge set, for each edge what is the. So here we have given a 3 uniform hypergraph, not necessarily, not a complete one. So now here is the general form of Ramsey theorem. So it says the existence of a positive integer RT now, right? Because we are talking specifically about T uniform hypergraphs. RT of n1 to nk, the smallest number such that any k coloring of the hyper edges, right? So now instead of coloring the edges, we are coloring the hyper edges, right? All this, this thing I will color with color. Let's say red. This will color with blue. This color again red. Maybe this also red, right? Something like that. So any k coloring of the hyper edges of KPT contains, right, KNIT of color CI for some I. Okay. So KN1T of color C1, KN2T of color C2, etc. K NK T of color CK. One of these, for every P greater than or equal to RT of N1 to NK. Okay. So this K coloring, I will assume that the colors we have used are C1 to CK. Okay. So earlier we noted it. Here I am not writing it specifically. We will assume that the K coloring means that colors C1 to CK, just some index here. Okay, so that is the generalized form of Ramsey theorem. Okay. Now we want to see why this is a generalization of pigeonhole principle. Right? That is what we started with. Right? We started by saying that we are going to look at Ramsey theorem and say that it is a generalization of pigeonhole principle. Now, how do you see that? Can you think about a way to see this and relate it with the pigeonhole principle? So, if you want, think for a few minutes by pausing the video and then continue later. So, first observation is that suppose t is equal to 1. So, when t is equal to 1, what happens? Then we are looking at one uniform hypergraph, which means that we have just vertices, and every vertex, you have an edge, right, by itself, which means that there is nothing happening, just the set itself, right? There is nothing else really there, right? We can say that which of them belongs to edges, but that's it. But if you are looking at complete graph, then of course all of them are basically edges. So I'm looking at one uniform hypergraph R1 of N1 to Nk. Say that I want N1 vertices of the color 1 and 2 vertices of the color 2 or Nk vertices of color k, right? But this is something that we already saw, right? What we saw was that, like, if you were coloring, let's say, n1 plus n2 plus etc plus nk minus k plus 1 vertices with colors c1 to ck, then at least one of them, right, like will have this property that n1 with color 1 or n2 with color 2 or nk with color k. See, basically coloring and putting into boxes are the same thing, right? Let us say just label the boxes, k boxes, k1, box 1, box 2, etc. with colors c1, c2, etc. ck. So when I put balls into boxes one by one, that is by saying that, okay, I'm coloring these balls or the set elements, right, whatever it is, with colors. So I have a k coloring now. Then we are saying that, okay, what we have by PHP is that if you have n1 plus n2 plus etc and k minus k plus 1 total vertices in the graph, then or total elements in the set, and your total balls that you are going to put into k boxes, then one of the boxes will contain at least n1, right, or of the same first color, or n2 of the second color, etc., nk of the last color. So this was generalized form of PHP, right? So we can see that even for just t is equal to 1, what we get is something in the form of generalized form of P general principle. So now we can see what happens, in terms of t. It is not exactly in the same statement, but you can see that why it is a generalization, right? So that is it. So Ramsey theorem is a generalization of P general principle. Okay, so we want to wind up this section by stating something which doesn't look like P general principle, but has some flavors of it. So this is called averaging principle. Okay, this is also a very useful tool. We will not use it at this moment, but we will see that it can be used to show some very amazing results by generalizing into what is called probabilistic method. The same idea, but slight improvisation. So here is the averaging method. Suppose I give you numbers, let's say, I don't know which numbers, I don't tell you, right? I tell you that I give you that I have some collection of numbers. I don't even tell you how many numbers, but I tell you that the average of these numbers is something like, let's say, alpha, or like 27. Okay, suppose I tell you that average of set of numbers that I have is 27. What can you say from this information that I give you, right? If I give you that the average is 27, then you know that there must be at least one number whose value is greater than or equal to 27. Because if every number is strictly less than 27, the average will be strictly less than 27. Right? Similarly, you also know that there is always some number whose value is less than or equal to 27. Because if everything is strictly greater than 27, then also the average will be strictly greater than 27. Right? Without knowing anything about how many numbers are there, what kind of numbers we have there, anything, we can still say this information from just the average. So this is called the averaging principle. Okay. So given that alpha belongs to real numbers, or is the average of a given set of numbers, we can conclude that the set contains some element x whose value is greater than or equal to alpha, and some element y whose value is less than or equal to alpha. Of course, they can all be equal to alpha. That's okay. Now, as I told you, this can lead to some powerful techniques like probabilistic method. Now, suppose I tell you that, I give you a little more information, right? I tell you that the average of a set of integers is 7.5. Right? If average of a set of integers is 7.5. Then you know that there is at least one number whose value is greater than or equal to 8. And one number whose value is less than or equal to 7. Right? This is also something that you can say. Okay. So with that, we we finish this part.